The comparison test can be used to determine if an infinite series AN converges by comparing it against another series Bn whose convergence is known. So for example, the geometric and harmonic P series, which are typically used to compare against in this test. And if all the terms in series A are smaller than or equal to all the terms in series B, for all n greater than some integer, and Bn converges, then An also converges. So really have to think about this. And in contrast, if all the terms in series A are greater than or equal to all the terms in series B, for some n greater than n, and the series Bn diverges, then the series A also diverges. And we'll apply this to practice problems. The limit comparison test is particularly useful for a series A, where An is a rational function of n. And again, we compare this infinite series against an infinite series whose convergence is already known, like the geometric and harmonic P series, which are typical. Now, given these two series have all positive terms, for all n greater than some positive integer, and Bn is not equal to 0 because we can't divide by 0, we have three rules in a limit comparison test. And these take some getting used to by applying them to different examples. So if the ratio of An and Bn as n approaches infinity is equal to a positive number, then both series An and Bn converge or diverge. And for the second rule, if the limit of An on Bn as n approaches infinity is equal to 0, and Bn converges, then An also converges. And if the limit of An on Bn as n approaches infinity is unbounded, and Bn diverges, then An also diverges. And we'll get some practice in applying this test to get the hang of it. Determine if the following series converges using the comparison test. So as n becomes very large, this term will dominate, and we can compare this series with a series that we already know. So that's going to be the harmonic P series. And we can take the constants outside the series, so this can be written as follows. And this here is a harmonic P series with the exponent P greater than 1. So we know that this series converges. And if we designate these terms in the series as An, then we can see that these terms here are always going to be smaller than Bn for all n. So therefore, due to this condition, and because our series here converges, then this series also converges by the comparison test. Let's determine if this series converges using the comparison test. So for a large n, we recognize that the first term is dominant, and we might write this as the following series. And now we know this here is a harmonic P series with the exponent P being less than 1, so we know that this diverges. And therefore, by comparison, we can see that the terms in the first series are going to be greater than those terms in that second series for all n, because we're subtracting 1 in the denominator. So therefore, because of this condition, and because this series diverges, then this series also diverges by comparison. Let's determine if the following series converges using the comparison test. So for a large n, this term dominates, and we may write the following series to compare against. And you may recognize this as the geometric series if we expand a few terms. So the general form of the geometric series is as follows, where a is equal to 1/3, and the ratio r is also equal to 1/3. So because the absolute value of the ratio is less than 1, then this geometric series converges. Now if we compare each term of both series, we can see that the terms in the first series are always less than the terms in the second series, for all n. So because of this condition, and because this series converges, then this series here also converges. Let's determine if the following series converges using the comparison test. So as n becomes large, we can see this term is dominant, and we can construct the following series to compare against. And if you expand this series, so we get 1 on 2 plus 1 on 2 squared, and so on. So you may now recognize this as a geometric series with a ratio of 1/2 and a equals 1/2. So because the absolute value of the ratio is less than 1, then where this series converges. Now the terms in our series here are always less than the terms in the geometric series for all n. So because of this condition, and because this series converges, then this series also converges. Let's determine if the following series converges using the limit comparison test. And this test is good to use when we have a rational polynomial. Now for a large n, the n cubed term will dominate in the denominator, so we can choose the following series to compare against. So we have 3n on n cubed, which is 3 on n squared. And now we take the limit as n approaches infinity of the ratio of both terms in both series. And now we can see the 3's cancel and the n squared goes in the numerator, so we get the following expression. And this evaluates to a limit of 1. So because we've got a positive number, so then rule 1 of this test applies, meaning that both series either converge or diverge. So if we check this series over here, and just take the constant outside, well, as we can see, this is a harmonic p series with the exponent greater than 1. So we know that this series converges, and therefore both series converge by the limit comparison test. Let's check if the following series converges by the limit comparison test. Well, for a large n squared in the denominator dominates, so this becomes 2n on n squared, or 2 on n. So we choose this series to compare against. And now we take the limit as n approaches infinity of the ratio of both terms in those series. So using a bit of algebra, this can be written as follows. Which evaluates to 1, which is greater than 0, so rule 1 of this test applies, which means that both series converge or diverge. So recognizing this series, by taking the constant out of the sum. Well, this is a harmonic p-series with an exponent of 1. So we know that this diverges. And therefore, by the limit comparison test, this series also diverges. Let's check if this series converges by the limit comparison test. Well, for a large n, this term dominates in a denominator, so we may compare against the following series. So that will be 3 on 6 to the power of n, or 1/2 to the n. And now we take the limit as n approaches infinity of the ratio of both terms in those series. And doing a bit of algebra, this simplifies as follows. And therefore this limit evaluates to 1, which is a finite number greater than 0, so both series either converge or diverge. And if you expand this series, well, this is a geometric series with a ratio of 1/2. And given that the absolute value of the ratio is less than 1, we know this geometric series converges. And by the limit comparison test, this series also converges. Determine if the following series converges using the limit comparison test. Well, we know that the natural log is always less than n to a positive exponent, as n goes to infinity. So we can conveniently choose the positive exponent of 1/2 and write the following series to compare against. So that will be n to the half on n to the 7 on 2, which is 1 on n cubed. And now we can take the limit as n approaches infinity of the ratio of both terms in those series. And doing a bit of algebra, this simplifies as follows. So n to the half grows faster than the natural log of n as n goes to infinity. Well, you can verify this using L'Hopital's rule. So we get a limit of 0. So the second rule of the test applies, meaning if this series converges, then so does this series. Well, this is a harmonic p-series with an exponent of 3, which is greater than 1, so we know this series converges. And therefore this series also converges by the limit comparison test.